right, the final thing we'll talk about is, it's called Theorem 8, but it's irrelevant, the number of it. It's a theorem of absolute convergence. All right, and it says, if the absolute value of a series, you throw absolute value bars around it, if that converges, then the series without absolute value also converges. Do you remember, okay, if I tell you something is differentiable, what's implied that you can also already know? Right, those two go together, but if I tell you it's continuous, is it guaranteed to be differentiable? No, okay. Similar here. If you can show absolute convergence, in other words, throw absolute value bars on it, take it, and if it converges, it is implied that the series will converge without the absolute values as well. But the converse is not true. Okay, the converse is not true. So if the absolute value does not converge, that doesn't mean that without absolute value that it will or won't converge. So it works one way but not the other. So this is called the theorem of absolute convergence. So what do we call it in the opposite case? So not divergence. If only the series without absolute value converges, but not the absolute value part. Then we call it conditional convergence. So if only the one without absolute value converges, but not that one, it is called conditional convergence. That's the final thing that we'll talk about. Okay, so the moral of the story is test the absolute convergence first. If the absolute convergence, if it converges, absolutely, boom, you're done. Everything will converge. It'll converge with or without. Okay, end of story. If you test the absolute convergence and it does not converge, then go ahead and check it without absolute value and see if that one converges, and then it would be called converging conditionally. So it would converge on the condition that you're not using absolute values. So let's do some actual problems with this. All right, so determine the convergence of the series sine of x to the n over n factorial as we go from 0 to infinity. All right, so we want to check for absolute convergence first. So we're going to just double check that. So we're going to throw absolute values around the sine of x. We don't need them around the factorial because those will always be positive anyway. So it's just the sine of x that we want to throw that onto. We're going to use a little direct comparison here. We did this yesterday. We actually did this problem without the absolute values yesterday and do it with the absolute values. So the direct comparison we're going to do is we know this will always be less than or equal to what? Yes, it will be less than 1 over the factorial. So this is what we did yesterday. we know that 1 over n factorial is 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus, and then from yesterday, do you remember what that does? It converges to e to the numerator, which is e to the first. So this will converge to approximately e. So it converges, yay, which proves that this thing converges absolutely. We don't have to check without the absolute values, because the theorem guarantees the implication. If it converges absolutely, then it will converge without the absolute values as well. And we actually showed that yesterday. We showed that was true as well. So we would say this series converges, and then we add the adjective absolutely, or it has absolute convergence. What it converges to, that's not what, we're not dealing with that. We're not dealing with what it converges to. We're just dealing with the fact that it does converge. Let's look at another one. No, because this converges both ways, right? Okay, another one. Determine the convergence. Okay, so does the following series n equals 0 to infinity of negative 1 to the n plus 1 over 1 over n converge absolutely? All right, well, let's check and see if it converges absolutely. So we'll throw absolute value bars around where it's needed. So where is it needed? Okay, on the negative 1 part. I don't really need it around the 1 over n because those will always be positive anyway. So we'll check. So n equals 0 to infinity. We're going to put absolute values around that. Yeah, we will. So if we put an absolute value around it, it will guarantee to always be 1. So then this will simplify to just be 1 over n. N equals 0 to infinity. 1 over n, whoops, we should have been starting at 1 as our lower number. We can't have 0 as my fault. Okay. All right, so we're going to have 1 plus a half plus a third plus a fourth, etc. plus dot, dot, dot. I told you the name of this series yesterday. Do you remember the name of it? It's called harmonic, right? This is called the harmonic series. And I haven't proved it to you yet. I'm excited to do that when we have a little more time, maybe on block day. But I did tell you that this harmonic series always does what? Diverges, okay? Yeah, it can be proved with the integral test, but there's another really cool algebraic proof as well. Come up with a French mathematician, so we'll talk about that if we have time. Divergent because of the integral test. The P series works because of the integral test. Yes, yes. Okay, and it's a harmonic series. Because the P-series test is defined at either greater than 1 or less than 1, and then we would prove the special case where it's equal to 1, and that has to be supported with the integral test, and then that name of that is the harmonic series. So that kind of gives us a corollary to the P-series test. It'd be better if you just went to its roots and called it the harmonic series. All right, so that's divergent. So that tells me it does not converge absolutely. So I do need to check the convergence of this without absolute value. So will it now converge conditionally? Or will it diverge in both cases? So we'll check n going from 1 to infinity, negative 1 to the n plus 1, 1 over n. So that series is going to be alternating. And so it's going to go 1 minus a half plus a third minus a fourth plus a fifth, etc. Okay, so by the alternating series test, this one will converge because it's alternating, its terms are decreasing, and its terms are approaching 0. And so the alternating series test shows that this converges. This one also has a name. It's called the alternating harmonic series. So you can cite it by its name as well. So the one before, you could just say it diverges because it's the harmonic series, and you could say this one converges because it's the alternating harmonic series. And so this one is going to fall into the category of what we would call converging conditionally, not absolutely, because only the one without absolute values converges. All right, so for the last 10 minutes, I want to summarize what we've done, try and do a final wrap-up summary of the whole chapter. All right, so kind of putting all of 10.4 and 10.5 together. I'm not going to go back to error, but I'm going to go back to interval and radius of convergence and try and put it all together. All right, summary. We're going to find the radius and the interval of convergence. So this is pulling us together for the quiz. After we've done that, determine the convergence is absolute or conditional. And then our last thing is to test the endpoints of the interval. And we haven't done that yet. Our radius and our interval of convergence has been an open interval, and so now we're going to be actually ready to test what's happening at the endpoints of the interval. Will it converge? Will it converge absolutely, or will it diverge? So this is I've got 3. I don't know if we're going to be able to get through all of them, but we'll get through as many as we can to kind of pull all of this together. All right, this series has x's and n's in it, so it's an algebraic series. We're going to go from 1 to infinity. It is x minus 3 to the n over 2n. So if we go back to the beginning of last week when we were just starting 10.4, to find the radius and the interval of an algebraic series, you have to perform the ratio test first. The result of the ratio test is going to form your radius of convergence. So we're going to start with the ratio test. So we're pulling it all together here. The ratio test says to take the limit as n approaches infinity of the n plus 1 term in ratio to the n term. So that would be x minus 3 to the n plus 1 over 2 times the quantity n plus 1 times the other term, the original term. And then we're going to clean that up. So we will reduce the x minus 3 to the n and the x minus 3 to the n plus 1. So that's going to give me 2n over 2n plus 2, and then the quantity left over, x minus 3. Using, this is infinity over infinity, so using L'Hopital, we will have the limit of 2 over 2 times x minus 3. And of course, 2 over 2 reduces, so we are left with x minus 3. So that is the result of the ratio test. We take the result of to find the radius and convergence, we take that, and we say that the absolute value for absolute convergence to happen, that has to be less than 1. So our radius right now is 1, because x is by itself. To find the interval of convergence, you'll remember that we separate this into, I take away the absolute value bars and add 3 to everything. So this is going to give me 2 less than x less than 4. And so then that's my interval of convergence. In fact, it's our interval of absolute convergence, because by definition, the interval starts out with those absolute values. So this is an interval of absolute convergence. Now, we want to find out what's happening at 2 itself, if 2 was the x value, and what would happen at 4 itself. So you want to check each of the endpoints. All right, what happens when x equals 2? So you go back to the original equation, or the original series, and plug 2 in. The original series was the series from 1 to infinity, and take the number 2 and substitute it in for x. I will get 2 minus 3 over n to the 2n, which is negative 1 to the n over 2n. Okay, what is that? It's an alternating. Okay, will it converge? Yes. Okay, by definition, an alternating series only converges conditionally. They don't converge absolutely. So this converges conditionally by the alternating series test. Okay. All right, so at 2, that's what would happen. Now let's check at 4. So go back to the original series and plug 4 in. 4 minus 3 to the n over 2n. That gives me 1 to the n over 2n, which is just 1 over 2n. What's that? Why? This is a form of the harmonic series. You could pull the 1/2 out to the front, and so this is harmonic, and harmonic always diverges. You could cite harmonic, you could cite the integral test. So we know we have absolute convergence of this integral. We have absolute convergence within the interval 2 to 4. At 2 itself, it'll conditionally converge still. And at 4, it diverges. 4 and up.
So that absolute convergence comes from
The definition of that we start with, we take the result of the ratio test and we put it in absolute values. And so that determines the absolute convergence. Okay. I have a couple, like 2 or 3 minutes. So I'm going to start the next one and we'll see how far we get. I might skip the ratio test and just tell you what the ratio test result is. Maybe that'll save us a little time. Okay, our next series is negative 1 to the n plus 1, which immediately you're like, ding, ding, ding. Okay, alternating series. And then the rest is x to the 2n over 2n. If you don't mind, I'm just going to do I'll tell you what the ratio test turns out to be. So the result of the ratio test is negative x squared. Are you okay to just believe me on that, just for the exercise of saving time? So we take the absolute value of that, and we set it less than 1. So our radius is 1. Then we drop the absolute values. We switch all the signs around. And we still get x is between 1 and negative 1. There's my interval. So we have absolute convergence within the interval of 1 to negative 1. Now you want to check your endpoints. So we'll check x equals negative 1. We will check x equals positive 1. So you take negative 1 and you plug it back into the original equation. You're going to get an alternating series, which converges conditionally. Okay, when I plug that in, I end up with negative 1 to the n plus 1 over 2n. We recognize that as alternating, and so it converges conditionally. By the alternating series test. The same exact thing happens when you put in 1, positive 1. You still get negative 1 to the n plus 1 over 2n. So it's the same thing. So to summarize, we will converge absolutely with x values between negative 1 and 1. We will converge conditionally at both 1 and positive 1. And then what if it's outside of that? What if it was like 7, x was 7? It diverges. So anything else is going to diverge. So you've got 3 types. You either diverge, you converge conditionally, or you converge absolutely. So we've got absolute convergence within the interval, conditional convergence at the endpoints, and divergence everywhere else.